Okay, sir. I think we can start, sir. It is on live.
Uh,
So, very good afternoon, very good evening to all present here. All the interns, I think the strength has increased to 90. So till today. So thank you so much. I think it is a day 4. Already, I think we have already met our Nagarajan sir, who is nothing but he's a chairman of IICC Chennai Regional Center. Also, he was like a AGM in the Petrofac, which is one of the famous design company across the world. Already, I think we have seen his introduction in the last part. So maybe without wasting time, I think we can get inside the session so that you can utilize your technical knowledge, technical expert from the sir in the evening of November 4th. So definitely thank you so much, sir, for joining today. I think the session of your today is going to be very important. As you already mentioned, it is going to be on process control system. Definitely, I think this is the one important field which is emerging across the globe for the chemical engineers as well as like instrumentation. But for as per chemical engineers, I think the total system is becoming automated, and so much of opportunities has been created across the world. And definitely, I think the final year students of chemical engineering should know the basics of process control. Then only I think when they go for any interview or even for appearance in the after 2-3 years also they can able to fetch up. And this field is very very important, and lots of opportunities is coming up in this field. So definitely this session is going to make you much more a valuable session. Thank you so much, sir. The session is over to you, sir.
Okay, thank you, Gokul, for the nice introduction. And I welcome all the students from the 5 engineering colleges and the staff members and other participants. Welcome to the second topic on process control systems. As Mr. Gokul rightly pointed out, that this is an important part of the process plant design. And as chemical engineers, we have to know more about the control systems, because we will be deciding the type of controls to be used in the process plant. So we should have a good sound knowledge of the instrumentation and process control topic. And I hope, I think we used to have in our curriculum an instrumentation and control subject. I hope after so many years now, definitely you all will have a subject on instrumentation and process control. So that is very important. So we will try to see the process control systems as being used in the industries. With that, I welcome you all again. Let us go into the presentation. So today's course and learning objectives is to get an overview of process control systems, to learn different types of control systems, to learn about various control loops and their functions, to learn about safety protection system. This is another important part of the control system. So we will see all these aspects one by one. So process control definition is, what is a process? Process is defined as a method of changing or refining the raw materials to generate products, okay, desired products. And Mother Nature has given us a lot of raw materials, which already the mankind is converting them into useful products. So then when there is a process to convert or refine raw material into various products, you definitely need to devise the process, and not only devise the process, develop the process, but also you should know the control systems for that, because anything uncontrolled is not productive and it will not yield the required results. You all know. So most of you are knowing about the automobiles, two-wheelers, whatever. You have controls. So the dashboard, you have all the meters. Speedometer is there, odometer is there, fuel gauge is there. Okay. So system performs. We should get the controls to effectively run the process and get the products. Okay. So the operating objectives or to control the process variables. We will see what are the variables. To control the process variables in a production process and to meet the operating objectives. Operating objectives is to get the maximum production and acceptable product purities and acceptable yields. Okay. So these are applicable to any process plant. So just I have listed some of them: oil and gas production facility, oil refining, petrochemicals, other process industries. So broad objectives of the process control is performance of the plant as per design objectives, that is reducing the variability. For any parameter, we keep a range of operation and we need to keep the range very narrow and minimize the variation in the parameter so that the process is steady, increasing the efficiency. So by using effectively the process control, you can increase the efficiency of the process. And then economics of the plant also is ensured by the operation, optimized operation and reducing the operating cost. Then reliability of the plant. If the control system is very effective, it will definitely lead to the reliability of the plant. You can rely on the process that you will get the required production at the required performance levels. So then most importantly, safe operation of the plant. So what are the control basics, process control basics? So you should understand the following process control requirements. Then you can design the process control system. Process objective. Any process has certain objectives. So you want to achieve certain things. Okay, from one stage to another stage, what are the desired changes that are to be affected? So that is process objective. So you have so much of raw material and you have to produce so much of products and at the purity levels. And then what should be the conversion? I want 80% conversion. So that means that is the process objective. Process operation is how we carry out this sequence of operations. In one of the earlier presentations, we have seen the block flow diagram. Like we prepare the feed, then subject it to the conversions, maybe reaction or just a distillation like unit operation. So the process operation steps have to be understood well. And what are the controlling parameters? Then the design and operational constraints. If we have any constraints, that also we should know, we should understand. Accordingly, we can design the process control system. Constraints may be like the composition of the feed. Okay, crude oil is having a very big family of hydrocarbons and the composition cannot be at one fixed point. Though we start the design with a particular composition of the crude and then derive the products. But the hydrocarbons are coming from the earth. Naturally, there will be variation in the composition. So that is like one constraint. So you should know the variations possible in the feed composition, and you have to input required measures to manage the process with varying feed composition. So that is one. That is an example for an operational constraint. Performance control is you have to get the required performance, run the equipment at the desired capacity levels, efficiency levels, and energy is another important thing. You have to manage the energy utilized in the process effectively, and no wastage of energy is advisable. So process control functions, I am showing you here both process control as well as the safety functions. So any process control, the control system in a process plant has two layers. One is called the control layer. Okay. Another one is the safety layer. So both are independent layers. So you should be very clear that we are not linking the layers. The control layer is continuously on operation 24/7, monitoring the various process variables and controlling them within the desired limits, and then lead to the production of the process. That is the process control layer. And second layer is plant safety. Plant safety, anything untoward happening in the plant, any pressure development in a vessel, or any fire happening in the plant. So those are called the hazards or emergency situations. So we should protect the plant and equipment against these emergency situations. We have safety layers like in safety instrumentation, we have fire detectors, gas detectors, smoke detectors. Then they will activate the mitigation systems. Okay. That is emergency shutdown system. And then mechanical devices also used to take care of such pressure developments. One is PSV, pressure safety valve. Most of you know, any equipment, pressure equipment will have the pressure safety valve, and the pressure safety valve is a mechanical device. It is not activated by any signal from the safety layer. It is mechanically devised so that it will open when the set pressure is reached, and it will release the excess pressure to the flare system. HIPS is a preventive measure. When the process is designed for certain operating pressure, if the incoming pressure from the outsource, means external source, is crossing the limits, then HIPS system will close the inlet to the plant itself. It will stop the flow of the fluids from the source to the plant. That is called HIPS. HIPS is high integrity pressure protection system. So these are the safety layers. Suppose even after all these precautions, the safety systems, devices, if something happens and fire happens, let us say fire occurs in the plant, then the next is the mitigation layer. Mitigation is the incident has occurred. We have to effectively control and contain the hazard. That is the mitigation measure. If it is a fire, there will be firefighting systems, active firefighting, fire tenders, and then you have fire water system and monitors. All those things will be put into operation, because any emergency there will be a huge alarm which will alert the not only the operating people but also the firefighting department. They will come with their equipment and fight the fire and contain the fire. Then if it goes beyond that, the next stage is first evacuate all the people, because the safety of people is the first priority. So people have to be evacuated safely. And if you are not able to control the escalation of the hazard, then you may have to abandon the place. That is called abandonment. So, but till the last minute, they will be doing the protection measures. So you have control layer, then safety layer, then finally the mitigation layer. The layers of safety, all the safety functions can be effectively achieved by multiple layers of safety protection. It starts from the design itself. Safety starts from the process design. One such thing is, just now I mentioned the pressure safety valves and high integrity pressure protection system. These are inbuilt in the process design. The devices are already in place. Then the process automation and controls, the process parameters, various operating parameters are being measured, monitored, and controlled in an automatic system. Then process alarms. During the process operation, if any of the parameters exceed, there will be an alarm. First, there will be an alarm to alert the operator to take care of the system upsets. But if the operator fails or if there is no immediate solution available, then it goes to the trip system, process safety trip. It will trip the plant, or it will trip the equipment, or it will trip the system, particular system. So this is a safety measure from the operation point of view. What are the active measures? Loss of containment and mitigation measures. If something happens, you have to stop stop the things flow out of the some pipe ruptures means the hydrocarbon liquid will be spreading around, correct? So you have to contain that. That is loss of containment. Mitigation is the next stage when the incident happens. You have to do the mitigation measures like firefighting, etc. So what are the process control variables? Just we take a very simple example of a tank, storage tank, where there is a, you can see there is an input, FO is coming into the tank. There is a head developed and maintained in the vessel. Then the flow is going out from the tank. So FO is the input, H is the head, and F is the flow going out of the tank. Variables are inlet flow, head in the tank, and outlet flow. Fixed things are tank dimensions are fixed. Okay, the pipe sizes are fixed. The pressure acting on the system is atmospheric pressure. That is also fixed. We have no control over them. For a steady state operation, F equal to FO. So if inlet flow is equal to outlet flow, the head will be remaining the same way. If FO increases and F reduces, head will increase. Similarly, if FO reduces and F increases, that means it will quickly empty the tank. So here there is no control. You can see there are no controls in this. Larger F is requires to keep the head in the tank. Okay, the flow larger F requires more liquid height in the tank. If you want to increase the outlet flow, you should have more head in the tank. Here we see the same tank system in a controlled environment. We have this tank which is covered and the liquid is coming in, the head is developed here. There is a level measuring mechanism here, level transmitter. So that is measuring the level, and the control signal from the measurement is acting on a control valve. So level control valve. This is called level controller. Level transmitter is the measuring device. And final control element is a control valve. If the level is more, it may ask the valve to open more and allow more flow. If level is less, this will ask the controller to reduce the valve opening, and then it will reduce the valve opening and allow the liquid flow to be reduced. So here the controlled variable is H. So depending upon the H, your control action is happening. Manipulated variable is, this is manipulated. Okay, you keep varying the opening of the valve so that the outlet can be managed depending upon the head available in the tank. This is a simple system, controlled system, level control system in a storage tank. So we just see a block flow diagram how this whole process system is operating. So process has some objectives. What we have seen already means it has to handle so much of capacity. It operates within certain pressure, temperature conditions. And now we have variables which are manipulated and controlled, which in the previous slide we and controlled variable is your head. Disturbance means there may be disturbance, external disturbances acting on the system, like atmospheric conditions. Okay, it has more effect in equipment like cooling towers and all. Rain or very hot weather will have effect on the cooling tower performance because it affects the humidity. So the manipulated variables and disturbances which get into the process, and we have the controls in place, then what we get is the controlled variables. A controlled process, again, a heating of oil by steam. Let us say we take the example of a heat exchanger. Oil is being fed to the heat exchanger. The oil is heated by steam, and the hot oil is coming out of the heat exchanger. We have a requirement of the oil temperature, outlet oil temperature. We have a requirement. Suppose it enters at let us say 40 degrees centigrade. We want to heat it to 150. So 150 is the requirement. 150 degrees centigrade is the requirement. There will be a sensor which measures the actual temperature, a thermometer like. Then that measured variable is passed through a temperature transmitter, which converts the measurements into a signal, okay, pneumatic signal. Signal goes to the controller, and the controller will have already fed the required value of 150 degrees centigrade. Set point will be there. So depending upon the variation, if it is let us say it suddenly goes to 160 degrees centigrade, then controller will measure the 160 and compare with the set point of 150. There is 10 degree more temperature in the outlet, so it will start closing the steam valve. It will allow the less steam to the heat exchanger till the comes down to 150. Similarly, if it is less than 150, say 140, the controller will open the steam valve more and allow more steam to go into the exchanger, and it happens still you reach the 150 point here. So this is how the process is controlled. This is a continuous control loop. It is happening continuously in the process. So what are the components in a typical control system? You have a temperature sensor. Okay, this is the measuring element. Measuring element sensor. Then the transmitter, which converts the measurement into a signal which is understood by the controller. This is the controller. Then this is the final control element. The control action is effected here. So this is the basic components in a typical control loop. So the same thing, that was a practical example. Here we see in the form of a block flow diagram how the whole process control system is operating. So process is the input, output, and disturbances. Okay, this is the process where you have input, output, and disturbances, and there is a measurement. So the variables are continuously measured, and then it goes to the evaluation step, which is nothing but the controller we have seen in the previous slide. So a set point is given already, like I said, 150 degrees centigrade for the hot oil outlet temperature. So that is the set point. So measurement, and then it is going to the evaluation stage where it is compared with the set point. Depending upon the variation, the control action is decided, and that acts through the control system. Okay, so that is how it is controlled. It is a final control element. And common terminologies which is very important to know in the control system. We have manipulated variables and controlled variables. Manipulated variable is you manipulate. Okay, it is like in a car when you drive, like an accelerator. If you want to go faster, you give more acceleration. If you want to reduce the speed, reduce the acceleration. Correct? That is the manipulation. By manipulating the accelerator, you can vary the speed of the car. Controlled variable is the speed, what you want to maintain. That is the controlled variable. Speed is the controlled variable. Acceleration is the manipulated variables. So variables that can be changed to control the process operation. Typically, flow rates of streams entering or leaving the process system. So it depends upon the type of process, which will be a manipulated variable, which is going to be the controlled variable. Usually outputs you have certain requirements, so that becomes the controlled variable. Other inputs coming into the process may be manipulated variables. So the controlled variables, usually you have 4 major parameters in any process plant: flow rates, composition, temperature, levels, and pressure. Total 5 controlled variables are there. Uncontrolled variables means the variables that are not controlled in a process operation, or that is beyond the control of the process. Means external conditions like weather condition, etc., or the feed composition, as I mentioned earlier, which is coming from some other source. The inputs to the process which is coming from other source, we have certain specifications. We also insist on the supplier to maintain those variables, but still they are subjected to variations. So these are all not in our control. They are called uncontrolled variables. And load disturbances is variables such as flow rates, composition, temperatures, and pressures of streams entering the process or leaving the process, which are set by the upstream or downstream of the plant. Because any equipment receives something from its upstream and then it sends its output to the downstream. So there can be load disturbances, the inputs can vary, or the requirement, the output is going to next process. If the next process is reducing its capacity, means that will affect your upstream equipment. So these are called load disturbances. Okay, somebody has to mute the mic, I think. A typical manipulated variable flow rate can be achieved by, how do you control the manipulated variable? Okay, for example, flow rate, controlling the valve position. So you have a flow control valve, you can vary the opening of the valve, either increase the opening or reduce the opening to achieve the required flow rate. Diversion of flow, sometimes we may have a branch line where you can divert some portion of the flow. This comes in bypass control. Okay, suppose the same heat exchanger example I will tell you. If suppose the oil temperature is going high in spite of your control, what will you do? You divert part of the inlet oil, bypass the heat exchanger, connect it directly to the outlet line. So some cold oil is going there, it will mix and then control the temperature. So this is called diversion of flow. Usually comes in the bypass controls. Motor speed, if you have a air cooler, a heat exchanger where cooling is affected by fans. So you can vary the motor speed, thus vary the airflow and control the heat exchanger duty. Damper position comes in the fired heaters where there is a flue gas is going out of the fired heater in a stack. There we put a valve. Damper is nothing but another valve. So you can adjust the damper position to allow the inlet air coming into the heater. That way you can control the heat transfer rate. Blade pitch is again for the fan. The fan blade pitch can be changed to vary the flow rate of the air. But blade pitch can be done only during maintenance. It cannot be done during the operation. Other things can be, other 4 parameters listed above can be done during the operation. We first see a open control loop, the input. So your input is coming here, there is a regulating valve which gets signal from the controller and it goes to the process and output. 2 control elements, there is a controller and a regulator, that is final control element. Timed controller operates regulator. You can put a timer there that may operate the controller, the timed controller. So every 10 minutes you see the opening and regulate, something like that. But there is no feedback or no control, there is no connection between the output and the controller. No assurance that output can be maintained at desired level because there is no measurement done, no feedback is going from the output to the controller. So controller is having some set point, it is just regulating the valve without comparing the actual output value. So here it is called the open loop where you don't have a precise control on the output. So normally we use closed control loops which are more effective. So this is a feedback control loop. Feedback means we have the process here, we measure the output variable, its value here, that is a sensor, a transmitter which converts the measured variable value into signal which goes to the comparator. The comparator compares the measured variable and the set point here. Reference value is nothing but a set point. Then the control action is decided here. That will either open or close the valve. Okay. So input is regulated based on the feedback coming from the output. This is called the feedback control loop. So we get the feedback from the output and use that to regulate the input. This is called the feedback control loop. So the action I have, whatever I explained is given in the words here. Most controls in the industry are feedback type because we are always interested in the output variable values. So most of the control systems in the process will be feedback type. So corrective action is taken by the controller here. So how the feedback control system works, the mechanism is measures the variable to be controlled that we have seen, compare the value with the set point, and depending upon the difference between set point and the output variable value, the control action is decided by the controller. In this case, this is called the feedback controller. And feedback controller acts on the manipulated variable, that is the inlet flow rate through the control valve. Feedback control loop of the drum temperature. This is some example. Okay, there is a steam is going there and heating the contents in that. This is the main input stream. So you measure the temperature with the then the comparator or the controller compares the measured temperature and the set point. Then accordingly it manipulates the steam. This is one example. And next important type of control loop is the feed forward. Okay, this is exactly the reverse. In the feed backward, we measure the output stream and regulate the input stream. Here, we measure the input stream. In some cases, the process is more dependent on the input variable, input parameters. So input itself we measure, and then through the transmitter takes it to the control block, and there is a value. Output has a set point. Here the set point is for the output. So the measured variable and the set point are compared. Accordingly, the control action is given to the control valve. It opens more or less according to the difference here. So this is a typical example of the feed forward. The requirement is here, and in advance we take the measurement and control. So this is called feed forward controller. So corrective action begins. Controller communicates the action to be taken by the regulator. So this is only in explanation is given here, whatever I told. And the example of feed forward control is there is a input stream coming here. Okay, this is the input to the process. This is the output to the process. Okay, there is a manipulated stream which is deciding the temperature of the output. Here, the input flow rate is controlled using the steam, which is steam is manipulated. Okay, so there is a ratio controller. So you have a final control element here. It keeps measuring the steam temperature, and then the inlet stream you have a set point. It measures that inlet stream flow rate, then it sends the set point to the flow controller here. Similarly, in a distillation column you have a temperature control loop. You want to maintain the temperature inside the column, and you measure the temperature here. You have a temperature element, a temperature transmitter, then it goes to the controller. Control signal is converted into pneumatic signal from electronic to pneumatic, because finally the valve will be operated by instrument air. Okay, so these are the elements: measuring element, transmitter, controller, and the IP converter. Okay, electronic to pneumatic converter, which finally acts on the steam inlet to the reboiler. So pressure control in a drum, you measure the same, instead of T we have P, pressure element, measuring element, pressure sensor, and then your transmitter. Then from transmitter signal goes to the controller, you will have the set point, and then the control action goes to the pressure control valve through the electronic pneumatic converter to open or close the valve according to the pressure to be maintained inside the vessel. Flow control on a pump, it can be feed forward or feed backward. This is a typical feed forward system, because we measure the discharge flow before the control element. Okay, so flow measurement using some flow meter, then flow control, electronic pneumatic converter, then the flow control valve. Level control loop is again, level is measured here, controller, IP converter, then goes to the control valve. So similarly, lot of things are there. Here we are analyzing the analysis water basin. This is a cooling tower. Cooling tower, we inject a lot of chemicals to maintain certain parameters in the cooling water. The algae should not form. Okay, so we inject some algae preventing chemicals. So makeup water is here. The cooling tower sump, the sample is taken, sample is analyzed, and analyzer results are passed through the transmitter, and then it goes to analyzer control. Parts per million. Usually these are very small doses. So that blow down. So when the chemicals composition is more, it starts discharging certain quantity of liquid. You add fresh water. Okay, this is the cooling tower circuit. So the blow down is controlled based on the chemical composition measurement in the sump water. And whatever is blown down, equal amount will be added as makeup water, because you want to maintain the system quantity. Cascade control is sometimes you have two variables being controlled and they are cascaded to control the final control element. So here there is a distillation column where temperature is measured, and that temperature measurement is fed to the flow control of the steam. Okay, so the temperature measurement not directly going into the control valve, it goes to the flow measurement device. You take the measurement of the flow, and you have a flow controller. Here similarly you have a temperature controller. These two controllers are linked, and then they decide the control action, and that is acting on the final control valve. This is called cascade control, because two variables you are measuring and use them to take one control action. Feed forward feedback control loops in a single process also possible. For example, here the heat exchanger outlet temperature is to be controlled. So you measure the outlet temperature here, heat exchanger outlet temperature, and then that is going to the control valve. To this analyzer control. I am sorry, this is not flow control. This is the analyzer. The analyzer results are going into the analyzer indicating controller, and the electronic signal is converted into pneumatic, and that is acting on the dosing chemical. Phosphoric acid being dosed into the. This is again something like, it looks like a cooling tower only. So this is a mixing vat. This is not the cooling. It is not the exchanger. This is a mixing vat. So I thought it was air cooled exchanger. No, it is a mixing vat, some chemical plant. So you add continuously certain chemicals. The dosage is decided by the output composition. Okay. Here it is feedback control. Here the soda ash is being added, which is the main raw material coming into the process. So soda ash flow rate is measured before the control element. Okay, you simply remember, if the measurement is before the control element, it is feed forward. If the measurement is after the control valve, that is feedback control and feed forward. So according to the flow rate measured upstream of the control valve, the signal is going to the flow indicating controller, where you have the set point, and that control action is decided, that will operate the valve. So you have feed forward controller and feed backward controller in the same process. These combinations are possible. And temperature flow cascade control loop, controlling crude oil temperature by manipulating the steam flow rate is shown. So this we have seen. I think heat transfer control is the main thing is your crude oil. Okay, crude oil is the main process stream. So main stream, a process stream, is the hydrocarbon, crude oil coming through the heat exchanger, and you use steam to heat the crude oil, and the steam condenses, and the condensate is trapped in a condensate part that is sent to the steam system back. So here the main thing is you measure the temperature of the output crude oil, then regulate the steam flow to the exchanger. Okay. So on simple, the condensate part level control is used to regulate the drainage from, and the control becomes more complex when you have number of equipments, more number of equipments. Here you can see there is pressure control in one vessel, pressure control in second vessel. The combined stream is going, and again they are divided into two streams. You have the flow control in each stream, but the configuration is same. Okay, it's a pressure control. This is cascade. This is a cascade control. You can see it's a cascade control. Pressure signal and flow signal both are measured and they are compared. The control action goes from the flow control to the control valve. So this is a cascade control of pressure and flow. This is a simple pressure control. This is a feedback control. You measure the pressure signal and then allow the excess pressure to the flare. Complex control loops, they are more sophisticated and complex than a simple and cascade controller. When you have so many variables in a process which are to be controlled in a simultaneous manner, let us say, then you have this kind of complex control loops. One is called split range control. You measure the variation and split the measured variable into two, say 0 to 50% and 50 to 100%. So 0 to 50% will be controlling one input and 50 to 100% will be controlling another input. So this is called split range, means you measure the parameter and the range is split into two. For one half of the range, it will operate one incoming parameter, other half will control another input parameter. Override control, sometimes we want to override particular control, you want to bypass. It's like something like a bypass control. Multi-mode controls, it's again the number of parameters are more and the variables are more, then you use the multi-mode controls. We'll see some examples here. Split range control is, this is nothing but hydrocarbon getting heated in a heat exchanger. Okay, the heat is coming from another equipment, from stabilizer side heater. There is another heater outside that is coming here. This is one parameter. Main flow from the slug catcher is passing through the exchanger. This is the main process flow stream. This is another stream which is used to heat the crude oil. So this, what we do, we want to control the temperature of the main process stream, the hydrocarbon stream. You measure the temperature here and try to control the bypass here. Okay, and as I said, the measurement is 1, but action is 2. Okay, for certain range, maybe half of the range, it will be directly controlling this one. Okay, main thing is you have to regulate the hot stream. Okay, one half it may be directly acting on this control valve and regulate the flow rate of this valve. But if suppose it is exceeding, as I said in one example, I said when the hot oil temperature is going more than 150, what we do? We bypass a cold stream and mix it with the outlet stream so that you achieve the required temperature here. This is the bypass control. So one controller is operating two control devices. This is the split range control. And split pressure control, controlling the pressure of the equipment, is shown here. So this is the main feed coming in the vessel. This is a separator vessel, medium pressure separator. There is a level control here, and level control, and this is a three-phase separator. The inlet stream has oil, gas, and water. So this is the two-phase compartment where water settles down, oil floats, oil overflows into the oil compartment, and that is taken out separately. There is an interface level control which is regulating the withdrawal of the water from this. Okay, this is the level control. The pressure control is here. This is the main gas outlet. Okay, and this is the excess pressure to the HP flare. Okay, this is a split range. So this measures as long as the pressure is within the operating pressure of this equipment, the flow will go through this. This will only control this valve. When the pressure exceeds the set point, what will happen? It will start allowing this valve to open and release the excess pressure to the flare. So the normal pressure stream will go here. The excess pressure will be released to this. A split range controller, and this is a normal level controller. A level control loop controlling level of slug catcher vessels is shown below. This I think we have seen two vessels are there, which are operating on the level controls on the water stream, and the hydrocarbon level controller on the two vessels is fed to the flow control here, and they are regulating the flow to the MP separator. The same thing, it is two streams, it is divided into two streams, and the level control from the separator vessel is linked with the flow control here. It's a cascade control, and then the control action is happening in the final control element after it passes through the heat exchanger. So the control functions may become complex depending upon the process, and mostly you will come across this kind of complex controls. This is a typical example of a complete system, right from the separator tanks and then to the two raw materials, component A and component B. On flow control, they are fed into the reactor. Reactor is heated by steam jacketed. So you have a temperature control on the jacket side for controlling the temperature of the reactor. And then the outlet from the reactor, there is a level control, and then this goes to the feed heater, it goes to the distillation column. So distillation column as a condenser reflex drum. Okay, the condenser is operating on the pressure control, and then the non-condensables or uncondensed vapors go out to the vent. The reflex drum operates on level controller. The product is taken out through the level controller, and there is a reflex which is controlled by the temperature inside the column. Okay, so this is the reboiler has the temperature control. We have seen this earlier, and column bottom flow rate is controlled by the level control here. Okay, this is the bottom product. The bottom product before going out of the column heats the incoming feed, and then it goes to the cooler, and then final bottom product comes here. So this is the complete process control in a unit. Okay. Now let us go into the control principles. First law is the best control system is the simplest one that will do the job. So what we are aiming at is, we already have seen there are process objectives. You have process variables and disturbances, and you have control variable, manipulated variable, all those things. But the best control system is the simplest one. Don't try to make a very complex control system. You start with the simplest one. When you have to handle more number of variables, then the complexity comes. Otherwise, the first law is to go for the simplest possible control loop. So complex loop of control looks great on paper, but end up in manual operation in industry. So it may look very beautiful in the paper and the drawing, but when they set up the plant and they start running the plant, operators may have problems. Sometimes the variables will not be cooperating. Maybe there will be hunting between two variables. That is called hunting. So you will, when you control the level, the flow may go out of control. When you control the flow, level may go out of control. This kind of things may happen if the control loop is not properly designed. So the second law is, must understand the process before you start designing the control system. This is very straightforward. You should know the system fully and how it performs. Then only you should decide on the control system. Okay. Many people try to use complex controllers to overcome ignorance about the process fundamentals, but they have failed. The third law is, liquid level must always be controlled, because liquid level is one dangerous parameter. If it is not controlled properly, either the vessel will be emptied or the vessel will be overfilled and leads to pressure build-up problems or spillage problems, all those things will happen. So liquid level is one important parameter. Mainly in the wherever we have liquid hold-up vessels, tanks, etc., columns, reflex drums, wherever we have liquid hold-up, the liquid level must be very carefully controlled. Okay? Structure of the control system must guarantee that liquid levels in tanks, column base, reflex drums are maintained between their maximum and minimum values. They are allowed to float between the maximum and minimum values. Control symbols will before that, controllers. There are different types of controllers. What we saw as a simple block in the drawing, controller has to perform the simple or complex mathematical functions to produce an output signal. Okay, so the controller does the very critical job. Important. It is like the brain of the whole control system. So it has been input with complex functions, mathematical functions, how to compare the measured variable with the set point, or how to decide on the final control action. There is a program is made and input into the controller. So that way controllers are very complex piece of equipment. So we have two types of common examples of controllers is programmable logic controller. PLCs. Logics are programmed to respond to inputs by sending an output to maintain the process at set point. Okay. This is doing the logic is inbuilt, means the logic we write. Usually process engineers write the control logic, how to control the level in the vessel. Okay. That control logic we write, that is given to the instrument engineer. The instrument engineer will configure the logic in the PLC, in the form of PLC. It is manufactured by some fabricators, not fabricators, the suppliers. There are companies which manufacture the PLCs. So from the design consultant, the control logic and the descriptions are sent and the variables are given to him. They input the logics into the controller, then it is called programmable logic controller. And another important control system is the distributed control system, which is very widely used in all the process industries. DCS are controllers that provide reading status of process, maintain database, and man-machine interface. PLC is one small piece of device which is controlling a particular parameter. Okay, but if you have 1,000 parameters in the plant, means you will have 1,000 PLCs. So, but DCS is the overall thing which takes care of the complete control of the plant, and it is a large database. It is a large database. It continuously has a recording of the measurement of various variables in the process, and also it helps in interfacing the man and machine. Means you have a control system, there should be an interface, correct? You should be able to operate the control system with the manpower, the operators. Okay, this provides the man-machine interface in addition to performing the control functions. So instrumentation uses a lot of symbols. I will quickly run through because this is a very this itself is another topic. Instrumentation and the P&IDs, piping and instrumentation diagrams, we use a lot of symbols for the control system. So usually the measured variable, it is in the field, a circle is shown, FT 123. Okay. A control loop, you will see the same number is maintained. This control loop has a serial number of 123. That means FT, pressure, flow transmitter, FT123. It goes to the your control block. This is called flow indicating controller, FIC 123. This is the DCS symbol. Circle inside the square is the DCS symbol. Then set point comes here. Okay, there is a temperature measurement. We are linking two variables here. Okay, temperature measurement TT123, and then TIC is temperature indicating controller. and then the set point goes here. The temperature set point goes here. According to the outlet temperature requirements, the flow has to be varied. You understand? So temperature is the controlled variable, and this should be maintained at certain level. So that temperature transmitter measures and gives the signal to a set point to the flow controller. The flow is adjusted to match the set point. So finally through the control valve. So this is the DCL symbol. The dotted line, I will tell you what are all the things. This is a shutdown valve, means the diamond inside square is a trip signal. Trip signal. Trip action is taken. If this symbol is shown, that means this device is used for shutting down. Shutdown. So the discrete instruments, a circle represents measuring instruments such as transmitters, sensors, and detectors. Okay, and the circle, there is a line in between. In the center, you have a line, means the location is in the control room. When there is another auxiliary parameter is there, double lines will be shown. And there is no line shown, simple circle means this is a field instrument. A simple circle with a dotted line is not accessible. Usually such instrumentation will be backside of the control panel. Okay. A shared control and display element means displayed and control types. This is the control room. It is displayed in the control room. A circle inside the square with a diagonal. And if you have the same field instrument with the DCS connected one, this is the circle in square. And again, this is behind the panel. You can remember, line means control room, no line means field, dotted line means behind the panel or not accessible by the operator, but instrument technicians have to access and do the repair work or maintenance. This is behind the panel where people normally won't go. And then flow and square root. The square root means the flow rate is a function of square root. So that is indicated here, square root function. The function of the variable is shown here, square root or square, whatever it is. Okay. So then we have controllers, computer functions. And nowadays all are like a master controller, which is like a computer. Okay. All, if you go to the control room, you will see a lot of monitors. Olden days, there will be a big panel. The diagram will be drawn. I mean, instruments are mounted on the diagram itself. The whole flow diagram will be in the control room. But now, all the system, whole process scheme comes on the monitors. Big size monitors will be used, maybe 24-inch size monitors. These are all like a computer, your desktop computers like that. So the controllers are indicated like this. Again, hexagon with line in the middle is control room. Double line is auxiliary. No line is field. And dotted line is not accessible, means it is backside of the panel. Hexagon represents computer functions. Those are carried out by the controller. PLC, we have seen programmable logic controllers. PLC types, again you will have same. The symbol varies, means diamond inside the square. There is a diagonal line means control room, double line means auxiliary, no lines mean field, not accessible means backside of the control panel. Final control element are valves, the pneumatic valve. If you see this kind of curved top, where the air pressure acts and which helps in opening or closing the valve, this is the pneumatic valve. Most of the automatic control valves are this type. Manual valve is manually you have to go on control, open or close. Electric valve means this may be a motor will be attached. So large size valves cannot be opened by pneumatic air, definitely not by human beings. So in such cases, you will have a motor. These are called motor operated valves. So electric valve. These are called actuators. This is the valve. The symbol above is the actuator. It shows whether it is pneumatic or manual or electrically operated. And there are a lot of signals we use in the piping and instrumentation diagram. And the process pipe is shown like this, process connection. Electrical signal is a dotted line. Pneumatic signal, that is a pressure. Instrument air is being used for opening or closing of the valves. So this is the horizontal line with two hatches at uniform interval. This is the pneumatic signal. Data link or something to do with the computer configured variable. This is called data link, serial data link. Capillary tubing is used by instrumentation for connecting the transmitter controller. This is called the capillary tubing for field systems. Inside you have some fluid, either hydraulic fluid or air, instrument air. Then hydraulic signal means the same type of thing, but here the actuating fluid is a high pressure oil, that is called a hydraulic system. And guided electromagnetic or sonic signal. So when something is operated with the sound waves, it is called sonic, and symbol is like this. So piping and connection symbols, which we have seen already. Heavy solid line represents piping. Thin solid line shows the process connection to the instruments. That is, a pressure gauge is mounted on the line, a thin solid line. That is called impulse piping. A dashed line, which I have already explained, electrical signals. Example, 4 to 20 milliampere signals. Slash line represents pneumatic signal where instrument air is going. Line with circles gives you data links. Other connection symbols are capillary tubing, example, remote diaphragm seals, hydraulic signal lines, electromagnetic or sonic signal lines, okay, which we have seen already. How do you identify the control functions? There is a tag number. As I told in the last presentation, in the process design, everything has to be numbered in a sequential manner from start to end of the process. So it is notified by a number. FIC is the identification letter. FIC means flow indicating controller. This is a DCS symbol. Okay. Dotted line shows some inaccessible thing. This is the tag number FIC 123. So number on behind ID symbols represent the instrument tag number. If the whole loop, flow indicating controller loop, the flow sensor will be FT123, controller is FIC123. Then it goes to the controller output to the valve will be FV123. Okay. Next diagram, we will see all those things. This diagram we have already seen. So this is called ISA symbology. This ISA is Instrument Society of America. So a lot of American standards are being used in the process industry, like API you must have heard of, American Petroleum Institute. Similarly, instrumentation control systems use Instrument Society of America. They have developed a symbology system which is being used by all the designers. Okay, this typical diagram we have already seen. Okay, means input tubing, thin line, then flow transmitter, and then flow indicating controller. Set my flow indicating controller that performs a square root of flow calculation. That is the square root shown here. This is the software data link. The temperature indicating controller. This is the PLC. Okay, and this is the DCS controller. Electric signal. This is the pneumatic line which is operating the valve. And simple field instrument, you will see a circle inside which you have TT123. The whole control is for one particular variable and connected variable. All will be having the same number. The ISA symbology, there is a big table. I am not going into the details of that. A to Z you can see. Okay. A to Z analysis, burner, combustion, voltage. Some are left to the user choice. You can fix whatever you want. E means voltage, F is flow rate, H means hand operated, I is electrical current, J is power, K is time schedule, L is level, and M and N, M and O are user choice. They are not assigned. You can assign if you want. And P is pressure, Q quantity, R is radiation, S is speed or frequency, T is temperature, U is multivariable controller, V is the vibration monitoring, vibration mechanical analysis, W is the weight or force, X is unclassified, Y is event, state or precise, Z is position. okay, position or dimension. Then we come into the ESD, okay, emergency shutdown system. This is an important second layer. I already told this has nothing to do with the process control layer. This is the second layer, protection layer for the process, which is called the emergency shutdown system. The purpose of the emergency shutdown is to ensure that the process is run in a safe manner with all provisions. And how this works, safe and timely shutdown of a process system when the control system can no longer maintain the process parameters. When the control system fails and the variables are going out of control, then they lead to a upset system, process upset, which may lead to a hazardous situation, and incidents or accidents may happen. In such a situation, ESD system comes into the picture and it will try to control and contain the hazards. So it will go to the trip mode. It will go to the shutdown of the system or equipment or the plant. So the initiators and final elements will be hardwired in ESD system. Instruments and control valves for control functions are normally not used in ESD. ESD sensors, controllers are separate. Okay, they are not linked to the process control, because we don't want to mess up with the two systems. One system, control system, is continuously in operation. That is the major thing which is running the process smoothly. ESD has to come into function only when there is an emergency. The objective of the ESD system is the three main objectives. Is first priority is to protect the personnel. The people working in the plant should be safely protected and evacuated in the event of an emergency. That is, protection of personnel is the first important requirement. Second is the minimizing impact on the environment. Means we should not affect the environment surrounding the plant. Okay, that is more important. We have seen many industrial accidents. The recent one was the styrene leak in LG polymer plant in the Visakhapatnam that affected people. Okay, the hazard doesn't stay in the plant alone. It spreads and affects the people living around. Okay, if it's a liquid spillage, liquid running out of the plant, means it may spoil the surrounding fields and all. Okay, so impact on the environment should be minimized. That is the second most important priority. Then third one is protection of plant assets. We should not aim at protecting the equipment and allowing the hazard to spread and affecting the people, etc. So first, to protect the people. Second, protect the environment. Third, you take care of the equipment, because equipment also is expensive. The equipment is damaged and damaged beyond repair. You have to buy a new equipment, means it is a expensive thing. So you have to protect the plant assets. So the priority, order of priority is like this. How ESD is achieved? Automatic sensing of an abnormal operation. That is, let us say, gas leakage or liquid leakage, or there is some fire, you get some smoke or flame. There are detectors located at the important points where you feel there will be leakage, or all equipments will have these sensors. Smoke detectors, fire detectors. Okay. Even in the buildings, it is mandatory now. You must have seen in the buildings sensors, flame sensors, smoke sensors, etc. They will go and operate the deluge system. So water will be sprayed wherever there is a fire. Automatic reaction to the abnormal condition by shutting down or isolating, and where appropriate, depressuring. So what it will do, once it senses there is an abnormal condition, the sensors will send signals to the control system. So either you shut down that particular, wherever there is a problem, you shut down that, isolate that, close the inlet and outlet valves. They are called shutdown valves. Close the inlet outlet and isolate the equipment, and then take it for the next step, next action. Okay. Vessel is isolated. There will be water pouring on the equipment to contain the fire, and sometimes we go to depressurizing. We don't want the hazardous material inside the equipment to remain there. So you depressurize, open the blowdown valves and allow all the hydrocarbons to escape through the flare, not to the atmosphere. Any release from the process unit should be routed to the flare where it will be safely burnt. Of course, it has some air pollution problem, but it will not affect the environment so much. And then you have visual system, means alarms will come, you will see lights, blinking lights, and then hooter sounds, alarm sounds. There are different sound levels depending upon the type of the hazard, and that is part of the safety system design. So this is to alert the personnel and take appropriate action. The ESD system has different levels. ESD level 1 is the highest level of emergency shutdown. That is a major hazard has happened. Some big equipment failed, or some tank ruptured, and a lot of hydrocarbons are leaking out of the tank and catching fire. This kind of major hazardous situation is called ESD level 1. In that time, the entire plant will be shut down, and the hydrocarbons contained in the equipment and tanks will be safely depressurized and sent to the flare. ESD level 2 is a plant shutdown without depressurization. The type of upset or type of hazard is not that serious, so you can just shut down the plant, isolate the equipment, and keep them in the pressurized condition. So when the problem is solved, then you can start the plant without any problem. If you totally depressurize, again commissioning of the plant has to happen. That will take some time. So it is loss of production. So only when there is most emergency conditions, ESD level 1 will be activated. Otherwise, ESD level 2. Level 3 is for a small unit, one unit, production train. One unit is being isolated and shut down. ESD level 4 is one equipment is in problem, one column is in problem, or one vessel is in problem. These are called individual process equipment. This is of minor nature, ESD level 4. And now we see PSV and high integrity pressure protection system. As I mentioned earlier, safety valve is a mechanical device which automatically releases the containment from the pressurized equipment or piping. Example, boiler, pressure vessel, etc. This releases the hazardous material to the flare system. This acts on the set pressure. There is a set pressure input into the valve, which is actuated by a spring-loaded safety valve. So the spring will be lifted when the pressure exceeds the set point and opens the valve and allows the excess pressure to the flare. Once the pressure is relieved, then the valve has to be reset. Okay. This is more reliable, and this is not acting on any external signal, control signal. This is a mechanical device. It has been found to be the most reliable device to protect the process system. Okay. So you will find on all the pressure equipment, you will have the pressure safety valve. It leads to loss of containment, means naturally you have to lose something to safeguard the equipment or unit. You will lose some hydrocarbons to the flare. High integrity pressure protection system is nothing but a highly safety instrumented system. It comes under safety instrumented system. It is designed to prevent over pressurization of a plant. This usually, as I said earlier, comes in the entry point of the plant. Okay, suppose we get hydrocarbons, crude oil or gas from the wells, let us say. So when the well control is lost, and then suddenly the entire stream coming into the plant is at a well reservoir pressure, maybe which may be 100 bar, but your plant is designed for 25 bar, let us say. Then if there is no protection in the inlet, then your plant will see 100 bar pressure. All the equipment will fail because we have designed the plant for 25 bar pressure. If suddenly it is like a very high voltage coming into the house, okay, instead of 230 volts, if you suddenly get 350 volts, 400 volts, all your electrical system will fail. All the electrical equipment will be damaged. This is something similar to that. So how do we prevent that? We put a pressure protection system. High integrity pressure protection system is nothing but a set of valves. Two valves, they are specially designed valves, very costly valves, and they will close. They will close. In the event they measure the pressure beyond a set point, then immediately they will close and isolate the total plant. This is called HIP system. And this doesn't lead to any loss of containment because it stops the input itself. So this is the equipment PSV. I think it may be legible to some extent. This is the separator vessel and liquid inside, and you have gas phase. This is the gas outlet. And there is a pressure safety valve independently mounted on the vessel. Okay. And it is a mechanical device. And most of the times we put two valves, two parallel valves. One will be online always, another one will be inlet is closed, outlet is always open, and that is releasing to the flare. Okay. This is a typical safety valve, PSV. High integrity pressure protection system, I told you, this is the inlet to the plant. Okay. HIPPS, high integrity pressure protection, is nothing but two valves together. Even if one valve fails, other one will take care. That's why we have put two valves, and they will shut down. They will close in the event of sensing high pressure in the inlet stream. So this is called HIP system. Okay, there are two trains. That's why we have shown two HIPS valves. Okay, that comes to the completion of the session, and thank you all for your patient hearing. And now you can shoot out your questions. And this time on the slide, I have given my name and phone number and mail ID. In case if any of you wants to get in touch with me, you can use this contact information. Yes,
sir.
Gokul, you have questions?
Thank you so much, sir. I think it is not so easy subject of process control, and maybe I think final year, I think they have already covered the subject on the basic. Maybe they would have understand, but not much to the deep. If at all they like the subject, first the likeness should come on the process control. Otherwise, it will become so dry. Definitely, I think your session would have given them like different areas you have shown, including safety and other related from design. Maybe I think a few people might be interested on process control, or few people on production. They may be like got much more information what they have not seen in the book, because these are all they cannot see. I think book only definitions and a few diagrams and some problems would be there. But this is very very deep, and they can easily understand, and they can able to correlate with themselves to industry level. Thank you so much once again, sir. Maybe I think a QA session can be opened.
Now, one more thing, there are good books. Kafner and Kopel was the book we used to read during our time. There are good books on process control. I have not totally covered. There is 3 modes of control: proportional, integral, and derivative. So that I have not gone into it. As you said, it becomes too much. So that they must have studied in their textbooks. The combination of the control modes, it can be simple proportional mode, or a combination of proportional and integral mode, or some complex controls. You will have all the 3 together: proportional, integral, and derivative mode, PID, they say. And the chemical engineers are the best fit for the companies who design the control systems. Like Honeywell is there. In India, it is Tata Honeywell. Foxborough, lot of companies which design the total control system of the plant. They prefer chemical engineers because this is entirely for the process. So people who understand the process are chemical engineers. They are more suitable in writing the logics and all. We have seen PLCs, correct? So writing logics and all is easy for a process engineer. Okay. And most of the control functions, they are all complex. And if you go back to the background of these things, you will have a lot of partial differential equations, different mathematical equations, which have to be input into the program. So the chemical engineers have another avenue into the process control system design companies also. So people who are interested may opt for that also.
Sir?
Yeah.
Sir?
Yeah.
Arun, sir.
Yeah, Arun,
I
you
have
can.
one. Sir, I have one question, sir. Actually, in open control loop, in third point, I have doubts, sir.
Hmm.
You showed no assurance that output can be maintained at the desired level, sir.
Hmm.
Um,
We may not use it in the industry. This is for understanding. I told. For example, you have a water overhead tank in the home, correct? You have a sump and then pump. You pump the water to the overhead tank, and then that is by gravity distributed inside the house. Okay. It is
okay.
open. You put the motor. You forgot. What happens?
Uh,
The tank is overfilled and overflows. Or
uh,
sometimes we forget. At the house every day we do. We run the motor for depending upon the tank size. We run the motor for half an hour or so. Okay, if you forget, it overfills and overflows. If you forgot to switch on the motor for 1 or 2 days, your tank is dried, so you don't get water in the home. So the typical example of the open loop is your household water distribution.
Sir, actually, we used timed control operates regulator, sir. So
Uh-huh.
actually, we fix the time. The for
We can do
the
that. Now, you are
sir,
right. Nowadays, there are
uh,
companies which offer the level control system for even household water systems. It is available.
okay,
There is a
okay,
level
sir.
control, and but only problem is the level control. What it will do, it will depending upon the level. It keeps on and off the motor. that,
Oh, okay,
that is not very
sir.
industrial environment. It is okay, but domestic environment it may not be that good.
Okay, sir. Actually, you said the feedback controller is not used. That's why we did not get the required level, sir, output. Uh,
A feedback controller.
Sir, actually, you said no assurance that output can be maintained at the desired
Decide
level,
level.
sir,
That is
because of we don't use feedback control, sir.
no, no,
We
we are not using any control. You are not.
actually I tell one thing, sir. Actually, we feed on things. Like we decide feed like a, sir. It goes to process enough to it get output enough to 10 minutes enough to get product, sir. Here don't need to go feedback processor.
This you can do manual. What I say, you don't need to go for a sensor, controller, all those things. It is simple in the lab. I would say in the lab you do a lot of fluid flow experiments and all. There you keep watching the tank. You regulate the valve, correct? When you
Yeah,
do
sir.
the fluid flow experiments in the lab, we mostly it is only manual. There is nothing like sensor and all. Okay, so you measure the flow rate through the pipe from a tank. So you have a flow meter, correct? You
Yes,
keep
sir.
varying the flow rate by a manual valve. You adjust that, or you can vary the head. You can vary the head and see how it affects the flow rate. Naturally, when head is more, flow rate is more. When head reduces, flow rate reduces. This you want to establish in the laboratory environment. You will have to do all those valve operations manually.
Okay. Thank you,
That
sir.
yeah, that is just to help you out. That what we study in the college is mostly the open loop systems. There may be I don't know. Today, some colleges have gone to very advanced stage. They might have got some automatic controllers installed and all. Otherwise, it used to be mostly manual. Yeah. Yes, Arun, you are clear.
Yes, sir. Yes, sir. Thank you so much, sir.
Yes, sir. I think a few queries have been in the chat box.
Mhm.
Maybe from the Abdul Rahman has asked, floating chamber is used for what, sir?
Floating chamber. I don't remember. I have used floating chamber anywhere. No.
Maybe Abdul Rahman, you can unmute, you can ask, I think.
What do you mean by
Sir,
floating?
sir, the level controlling, I think so, is used for that, or like that is used floating in petroleum field, sir. In
Floating
petroleum,
chamber. Hi, are you talking about level control?
I think so. It may be level control. I don't know
Yeah.
properly how much
What
I must
happens?
be.
We use what is called a stilling tube, and inside there is a float. This is basically a float controller. Float means the simplest example I can tell you is the toilet flush, you know, in the house. Toilet flush, you open and see there will be a ball floating on the water, correct?
Yes, sir.
That is the float. When you flush the toilet, water is totally drained. The ball goes down. When the ball goes down, it opens the inlet valve. When the flush tank is filled to the required level, the ball is coming up and it closes the inlet. This is the float type of valve. The simplest example is our household toilet flushing mechanism. In industries, large tanks and all, what they do, they same float controller we used to float type level controller. Okay, and there is a stilling tube. The surface disturbances, if a large tank, there may be surface disturbances. So what they do, they put a tube, means a metallic pipe, inside which the metallic pipe is inside the tank. It is open at top and bottom. The water level, whatever is outside the tube, it is inside also. Okay? The float is put inside the tube and it is connected to the controller. So as the float moves up and down, the level is indicated outside the tank. You are right. This is called, there are different types of level control instruments. This is a float type. There is one more measurement is DP transmitter. They say DP, differential pressure transmitter. This device will be mounted at the bottom of the tank. So the whole hydraulic head will be acting on this, correct? So when the head varies, there is a diaphragm in the instrument. So one side is seeing the atmospheric pressure, other side is seeing the hydraulic head, the pressure due to the head on the vessel. So this differential pressure is interpreted and calibrated as the level. So this is called a DP level controller. So different types are there. Level non-contact level controllers are there. So in mostly in nuclear industries and all, they use non-contact level controllers. So the different types are there. That's a big subject. If you go into the construction of the instruments, that itself is another topic, you can say.
Okay, sir. Okay, sir. Thank you, sir.
Okay, Abdul.
Yes, sir. We have one more, I think, from Magesh. In why exact steering leaks at the time of EST level 1 is worked or not?
That I really don't know. We have to go. I think the report is out. The a committee was formed. They did the investigation, and the report has been published. It is available public. In one of the webinars, I saw somebody was presenting the Vizag incident report itself. So they analyzed a lot of parameters. Ultimately, they have to go to the shutdown only, because when it is affecting the people and the environment, they must have gone definitely to the shutdown, total shutdown. But by the time they took shutdown, the incident escalated and spread around the area. So the only way is to shut down the plant. Yes.
Yes, sir. Fine. So I think, intern, any more queries? I think you can ask. I think one has come from Muthumayal. Muthumayal, I think you can hereafter put it questions for everyone. Sir, are the control system valve in an industry are connected through Wi-Fi or internet? How are the engineers able to control the operation just by using DCS?
DCS only. Wi-Fi or operating through phone you cannot do in a complex plant. Okay. This will be sitting in the control room. They will be able to open the control valve more or less. You can take it on manual, and in olden days, operator has to go to the field and then do the operation. Now the control systems are very sophisticated, and nowadays the operators have a very good life because they are sitting in the controlled atmosphere, air conditioned atmosphere inside the control room, and just look at the monitor, keep seeing the variables, and it's just like what you do in your computer laptop. The same way they control. They can vary the controller position, controller variability, opening and closing of the valve. You can adjust. If it is a 80% opening, if you want to make it 70%, you can make it 70%. Looking at the output, so that is possible now, but not through Wi-Fi or phone. I don't think. I have seen some people have done the switching on pump sets in the field, in the agriculture field. The people have some good persons have they invented a device. You can start the motor through your mobile phone with a device, okay, without going to the field. That's also possible, but not in the industrial plant.
Yes, sir.
Okay, Magesh, anything?
Yes, I think.
Okay, I think.
Yes, sir. Maybe one is there.
Tell.
Chandrasekharan, I think he asked, should I master the subject to become a safety engineer?
Safety is another part of the control system we have seen. Control system is for continuously monitoring, controlling the plant performance, whereas safety comes only when there is an emergency, but the system is always on. ESD system is always on. It is actively looking into the plant. It is like your CCTV camera. Okay, CCTV camera is sitting there and keep watching and recording the happenings in that vicinity. Same way, ESD system, it has all the detectors, uh, control elements, deluge system, which allows the water to pour on the equipment if it comes on fire. So those things are all active only, but they are not coming into operation unless there is a emergency. So for safety engineer, I think if you can do some courses, I don't know, there may be courses in Google, if you can guide him,
Yeah, yeah.
some
Yes, sir.
diploma courses or something like that is there.
Yes,
So
sir. I think.
when you study the course, automatically the safety systems will come there. Means
Yeah.
escape route, so many other things. This is measurement and upset control is one, and apart from that, there are others. Safety fire water system you have to design. Determine the load on the fire water, how much fire water will be required in the plant. That's called fire water hydraulics. All those things are part and parcel of HSC design. Yeah. But with chemical engineering background, you can easily learn those things. They're all much easier compared to your process engineering design.
Sure, sir. Thank you. Thank you so much, sir. I think definitely. We have our Dr. Balamurugan, who is also like a Tamil Nadu State Center committee member and ex officio of IEA TVLC. Can Balamurugan can give some felicitation for sir?
Yes, thank you so
Thank
much,
you.
Dr.
Welcome, Mr. Balamurugan.
Sir, thank you so
Welcome,
much, sir.
Dr. Balamurugan. Dr. Balamurugan.
Yes, sir. Nice presentation, sir. So I joined the presentation and I could see that the insight, whatever you have given, is a layman approach where any individual who is not even a chemical engineer can follow it, or an engineering perspective. It was an exorbitant idea.
Oh, thank you. Thank you so much.
Yes, sir. So it was wonderful session, sir. And also the people who have interacted, they could see that they have keenly watched and they have observed all such things, and such people have queried on it. That too, the budding engineers have an idea of how to get into the mastery part of all such process management and other engineering process. And that is a very great move, sir. So this is a wonderful opportunity where the people where they could not even move to the premises, but they could see that, visualize from such a experienced personality that this is how the things are working on, and you could make it view the actual scenario. This is how the float is. You have given a example.
Yeah, float, that person.
And other things. So it is a
So,
simple thing that even they come to the plant, they could see only the big large mass of equipments, but not as a theory digested. But whatever examples you have given, it was wonderful, and they could see that it is been visualized actually. So
actually,
wonderful.
I used to give very common examples. The float level controller,
Yes,
your
sir.
toilet flush tank is the best.
Yes, sir. The second example, whatever you give. So it was wonderful,
Similarly, in
sir.
the car, if you want to speed up, give more acceleration. or
Great, sir.
reduce the acceleration, speed comes down, all those things. These are manipulated variable. Speed is your requirement.
Yes, sir.
That is a controlled variable. Manipulation is your accelerator. You
Yes,
increase.
sir.
These things will definitely